In this lecture, we discuss the integrator and differentiator using operational amplifier. Now, integrator. Now, definition of integrator is a circuit which the output voltage is the time integral of the input waveform. Input voltage waveform is called integrator. So now output is time integral of input is called the integrator. Now we will see the diagram. So now here I am taking the operational amplifier, which is having both inverting and non-inverting inputs. Now in ground I am making it to non-inverting terminal, I am making it to ground, and input I am connecting to the resistor, and here the feedback component is capacitor. Now this is C and this is R. Now here I am applying the Vs or V in. This is V in. We need to find out the V out. From the definition, it is directly proportional to the V out is directly proportional to the time integral of input signal. So now we need to derive the expression for this. So similarly, in the last circuits, how we have taken the notation for voltage. Now here I am taking it as a VA. Now here I am taking a VB. So now we derived that VA is equal to VB is equal to 0. This is a virtual ground concept. Now these two potentials are equal, and because VB is connected to the 0, so VA is equal to VB is equal to 0. This is equation number 1. And apply nodal analysis at node A. Now here if I apply nodal analysis, then how to write the expression? So now here for this branch current and this branch current we need to write. Now current flowing through the resistor, how can we write? I is equal to simply V by R. Now in this case when we are writing the we are taking the voltage, we have to take the potential difference, because here VA is there, here V in is there. So VA minus V in divided by R we are writing. Now coming to the capacitor. So how to calculate the current flowing through the capacitor means the current flowing through the capacitor IC or IF is equal to C into dV by dt. Now this is the current flowing through the resistor formula, this is the current flowing through the capacitor formula. Now what is V over here? V is VA minus V naught, that we have to write in the nodal expression. Only the difference is what? How to write the expression for the current in the flowing through the capacitor. Now here if I write the expression, then what I will get? VA minus V in divided by R plus, now for this C into dV by dt, where V is what? VA minus V naught divided by dt is equal to 0. Now wherever VA is there we need to substitute 0 from the equation number 1. Now from equation 1 we get, if we rewrite this, then we get minus V in by R is equal to C dV out by dt. Now both side, if we apply the now both side integrate the equation. Now this, if I take this as expression number 2, integrate expression number 2 both sides, then we get minus integral V in by R is equal to C V out by, now here C V out dt. Now here integrate with respect to dt, then we will get like this, and V naught is equal to, now here R is constant, and 1 we will get minus 1 divided by RC integral V in dt. Now here I have taken V in dt. Now this is the expression for the output. Output we got, so integral of input and with the constant of minus 1 by RC. This minus indicates the inverting, because here the signal is applied to the inverting terminal. So that's why we get the inverted output. Now if I take the sine wave, if I am applying the input sine wave, then what is this integration of sine? So now if this is the V in, Now integration sign is nothing but a minus cos, and already one more minus is there, so it is a plus cos. So now we get the expression like this. Now for 0 we get the 90, for 90 we get 0, again for 0 maximum, v minus max, and so like this we get. Now if you add all these points, then you get the plus cos sine waveform. Now this is V in and this is V out. So this is the waveform for the sine wave. When we apply the sine wave, we get the minus cos actually, but here we have a one more minus, that's why we are getting the plus cos. Now similarly, if we apply the square waveform, then what we get at the output? Now if you apply the square waveform, for square what is the expression? For square expression is constant. When you are integrating the constant, if I'm taking this as a, when you are integrating the a, then you will get what? A t. So here we are going to get the output waveform like this. Minus sign is there. For rising we get the falling. Now we get the falling, and now here falling, and for falling we get the rising of now this is the output. Now this is V in and this is V out. Here I have shown the for sine, integration of sine is equal to, I have shown, and integration of square is equal to I have shown. Similarly, if you apply the, we can also apply the triangle, at the time you will get the parabola. Now this is about the integrator. Now similarly we need to discuss about the differentiator. Now differentiator. Now what is the definition for the differentiator? So output is the differentiation of the input. Now here if you see the diagram, only the difference is interchanging the components of integrator. Now here input I am taking the capacitor, feedback component is resistor, and this is negative terminal, and positive terminal, inverting, non-inverting terminal make it to ground, inverting terminal we are applying the signal V in. Now output, here we need to find out the output. Output is differentiation of the input. It is directly proportional. We need to find out the constant. Now here C, I am taking capacitor name, I am giving it as a C, and feedback resistor is R. Now we need to find out the expression for this. So now here I am taking, now again here this node E, I am taking it as a VA, this node voltage I am taking it as a VB, and we know that virtual ground concept, VA is equal to VB is equal to, where VB is connected to the ground, that's why VA is also acts like a ground. This is equation number 1. Now after that apply nodal analysis at VA. So if you apply the nodal analysis, then what we get? Now here this current and this current is equal to nothing but a C into dVA minus V in divided by dt plus, now for this one, VA minus V naught divided by R is equal to 0. Now substitute equation 1 in equation 2. Now if you take this as a equation 2, substitute equation 1 in equation 2, then wherever the VA is there we need to put 0. So we get minus C dV in by dt is equal to V naught by R. Now what we want? We want V naught. So V naught is equal to minus RC dV in by dt. Now if you see the expression, output is directly proportional to the differentiation of the input. Hence we derived the, now here the proportionality constant is RC. This minus indicates, now here we apply the signal to the inverting terminal, that's why we get a minus sign at the output. Now if I apply the sine wave for this differentiator circuit, if this is my sine wave, then what is the differentiation of sine? So differentiation of sine is nothing but a cos, and here a minus sign is there, so we get the minus cos. So now here I am writing for 0 we get minus maximum, for maximum we get 0, and again for 0, for 180 degrees, now we get the plus maximum, 0, minus maximum, plus maximum. If we add all these points, then we get the cos waveform. So this is the output, V out, and this is the V in. So this is about the sine wave. Now similarly, if I apply the square waveform, then now here this is my square waveform, and so differentiation of constant is nothing but what? 0. We don't get any. So here you are going to get waveform like this. So here spikes. This is called as a spike. This is spike. So this is the output, V out, and this is V in. So square is nothing but what is, it's a constant. If magnitude is a magnitude, or if magnitude is 2 volts, or magnitude is 3 volts, then differentiation of 3 or differentiation of any constant is 0. That's why we get the spikes like this. So this is about the differentiator. Now with this we completed the operational amplifier. Now in this operational amplifier we have studied the inverting amplifier, non-inverting amplifier, adder, subtractor, integrator and differentiator. So in the next lecture we see the digital logic gates. Thank you.